Hi everyone, this is Mr. Hall and this is another video about GCSE chemistry. Today we're going to be talking about metal oxides. This is often the entry sort of content that you have to know before you start going into the world of redox chemistry and reactivity series. So this stuff's pretty important. So we'll just start with the basics of reduction and oxidation really in terms of their definitions today. So the objectives are to describe how metal oxides form, and also to define oxidation and reduction in terms of the gain or loss of oxygen. So first off, I just want you to think about a copper wire that's being placed inside the flame of a Bunsen burner. Now, if I leave that wire in a flame, let's say I weighed it at the start and the mass was 1.5 grams. If I leave it in that flame for quite a while, let's say several minutes, maybe an hour even, just a really long time, it'll eventually start getting a lot darker. You'll see this black powder forming on the outside of it, and then the mass might seem to increase. So if you weigh it at the end, it will have a larger mass than it had at the start, which seems quite unusual. So the question is, what's going on here? Why is the mass increasing? Why is it changing colour? Now, the reasons for that is explained by looking at the reaction itself. So at the beginning, I start with copper wire, which is just 2 lots of Cu, and that is my copper wire there. It reacts with oxygen from the atmosphere. Now I'm just going to write O2 here, and that oxygen obviously is from the equation, and that is in the air or the atmosphere and reacting with my copper wire. Now that forms copper oxide, which basically coats the outside of my wire. Inside it still might have some copper which is unreacted, but on the outside you'll have that copper oxide which is formed. So what you've got is mass being added to the reaction mixture from the atmosphere, and that gain in mass that you get, which is the 1.5 to 1.7, is essentially the mass of oxygen that's been added from the atmosphere to create that copper oxide. Now, that's one interesting thing as to why the mass seems to have increased. The other interesting thing to think about is actually what's going on in terms of oxygen moving. So let's have a look at this again by thinking about the particles. Now, if you have a look over here, I've tried to re-show you this reaction. But what we've now got is these particles which form a lattice. That is basically the copper wire which I've put into the Bunsen burner flame zoomed in. There's obviously billions and billions of atoms inside this lattice. I've only shown you a very small number. And then the blue particles which form these diatomic molecules, these are your oxygen molecules which are floating around in the atmosphere. Now as it reacts, these two combine, and initially what you'll have is a state where the atoms are quite far apart and not doing a great deal, and then they're going to start reforming the bonds to create your copper oxide like so. So as you can see, they start coming together to form this relatively large lattice, and this is basically your copper oxide. And what you can do is you can scrape it off the wire to form a powder. Now what's interesting is what you start with and what you end up with in terms of the states of matter. Now at the beginning, you start off with a copper wire, which is a solid, that's shown by the S here, and it's like a solid metallic wire, which is orange. That reacts with a clear colourless gas, which is oxygen, or you obviously can't see it in the atmosphere, and that's that bit, okay? And it's interesting how those two combine to form copper oxide, which is basically a black powdery solid, which is, in terms of properties, completely different to what it started with. Now, the copper here has been oxidized. But the question is, what does that actually mean? So let's go into the definitions of reduction and oxidation in a bit more depth. Now, reduction and oxidation are defined as follows. Now, I'm going to go through some very narrow definitions. You obviously have to do more complicated definitions if you do sort of like a higher level course. I'll just start with the basics today. So oxidation basically is the gain of oxygen, and reduction is the opposite, it's the loss of oxygen. As an example, let's have a look at the extraction of iron from its ore, which looks a little bit like this. Now, if you look at this reaction here, you'll see that, so I'm just getting my pen back up, that I've got iron oxide, which is here, and at the start you can see there's lots of oxygen attached to the iron. But as the reaction proceeds, I can see that it loses oxygen. Now, because it loses oxygen, that is consistent with our definition of reduction. Therefore, my iron has been reduced. Okay, so I say that's been reduced. However, if I look at my carbon, now the carbon starts off with 1 oxygen because it's carbon monoxide, but as the reaction proceeds, it gains another oxygen to form carbon dioxide. Therefore, this substance has been oxidized. Okay? Now this is a reaction where you've got reduction and oxidation happening at the same time. If you have reduction and oxidation happening at the same time, we call it redox reactions. Okay, so whenever I talk about redox, I'm talking about reactions where you have reduction and oxidation happening at once. Now, let's look at the definitions of these in more depth, and let's start with oxidation. Now, as I mentioned before, oxidation is a gain of oxygen. So, for example, if I've got magnesium reacting with oxygen in this equation here, I can see magnesium at the start doesn't have any oxygen attached to it. However, as the magnesium reacts, it gains oxygen. Therefore, that has been oxidized. Okay. Now, it's easy to see from that reaction that magnesium has gained oxygen. Therefore, an oxidation reaction has occurred. The magnesium has been oxidized. Let's have a look at reduction. Now, with reduction, let's have a look at the reaction of lead being extracted from lead oxide by reducing with carbon. Now, this is a reaction that you'll quite commonly get because it's quite a big industrial process, particularly with iron. So, in this reaction, I've got, so I'm just going to move my, there we go. In this reaction, I've got lead oxide here, and my lead starts with one oxygen attached to it. However, as the reaction proceeds, you can see that it ends up with no oxygen, so it's lost an oxygen atom. Because it's lost an oxygen atom, it's been reduced. At the same time, you can see my carbon has gained oxygen because it's gone from C to CO2. It's gained a couple of oxygen atoms. As a result, that has been oxidized. Okay, so the oxygen's been removed from the lead oxide. The lead oxide has been reduced. Okay, so let's practice this a bit more. You might want to kind of pause the video and have a go at this in order to see what's been oxidized and what's been reduced in all the equations. Pause it now if you want to do that, but I'm just going to rattle through what the answers are for each equation. So if I look at copper oxide and carbon, I can see that my copper oxide, and I'm going to look at the symbol equation a bit more easier. Copper oxide turns to copper. That's lost oxygen, therefore my copper has been reduced. However, my carbon has gained oxygen, therefore my carbon has been oxidized. Let's have a look at my second example. Iron oxide plus aluminium goes to iron plus aluminium oxide. My iron oxide, when it turns into iron, it's clearly lost oxygen. Therefore, my iron has been, I've not written that very well, my iron has been reduced. However, if you look at my aluminium has turned to aluminium oxide. It's clearly gained oxygen in this process. Therefore, my aluminium, oops, my bell, that's been oxidized. Okay, let's have a look at the others. So here, my carbon monoxide plus iron oxide turns into carbon dioxide plus iron. Let's start with the iron first of all. I go from FeO to Fe. You can see that this loses an oxygen as it goes from here to here. Therefore, my iron, because it's lost oxygen, that's been reduced. However, my carbon, it starts with one oxygen, but then turns into two. Therefore, my carbon has been oxidized because it's gained that extra oxygen atom. Let's do the last two. Zinc oxide plus hydrogen makes zinc plus water. Let's start with the zinc. My zinc starts off with one oxygen atom. It then ends up with none. Therefore, because it's lost oxygen, my zinc has been reduced. However, my hydrogen, it starts off with no oxygen atoms at all, but then gains an oxygen atom to form water. Therefore, that has been oxidized because it's gained oxygen. And then for the last example, magnesium and oxygen turn into magnesium oxide. Magnesium has gained oxygen in this process. Therefore, that has been oxidized. Now, technically, nothing has lost oxygen to be reduced, so I'm not going to discuss that in too much depth. When you get into more of the technicalities of what reduction oxidation is, you'll find out the oxygen has been reduced here, but that's something which I won't discuss today. But the main thing that I want you to take away really is that the magnesium has been oxidized in that particular reaction. And that's it. So I hope that's been helpful as an introduction to redox chemistry and metal oxides, and best of luck with your studies on this topic.